today, what I will do is that I will also introduce you to the concept of brightness or intensity of radiation. Luminosity was ergs per second. That's the energy generated per unit time. Flux density is ergs per second per unit area that you're either observing or radiating from the surface of a star. When you express that in terms of per steradian, you get what is intensity. So when you talk of black body radiation, when you talk about the brightness of the intensity, your units are ergs per second per centimeter squared per steradian. And if I talk about intensity at a particular frequency or wavelength, then I also have to put in per unit frequency or per unit wavelength. Often this could be in per unit angstroms. So one is the energy per unit time, per unit area, per unit frequency or wavelength, per unit steradian. Okay, so this is the standard definition of specific intensity. Energy and cos theta comes in because the surface at which you're inclined, at which you're observing, or the surface from which the radiation is going out need not be orthogonal to one another. So this is the angle theta, so that if you're talking of a situation where it is completely orthogonal, theta is equal to 0 and cos 0 is 1. Okay, but taking that area inclination into account, so your intensity or specific intensity in this particular case that I've written down for frequency is energy per unit time, per unit area, per unit frequency, per unit steradian. Okay, that's ergs per second per centimeter squared per hertz per steradian. So I knew the brightness of a source, whether it be emitting or observing, could depend on location, would depend on location in space. It would depend on the direction you're looking at. Even in a source, there could be large variations of brightness within a given source. For example, you remember that in the radio galaxy, which I showed you, Cygnus A, the hotspots were much brighter than the rest of the lobes. So within a source itself, there can be dependence on intensity. It will also depend on frequency because the flux density has a frequency dependence, and also different parts of a source, the spectrum may be different. And space, because different directions will have different intensities or brightness. The figure on the right just illustrates when it is normal to the line of sight, and in which case theta is 0, cos 0 is 1. Okay, and one of the very standard books on radiative processes, which you can study later, is Rubickian-Lightman, Radiative Process in Astrophysics. I've taken these two figures from there. But a lot of the discussion you'll find in Irwin as well as Caroline Osley, which is your best practice. Okay, now flux observed. Now let me see what I have written over here. I've defined intensity, which we have done already. Flux is equal to I cosine theta d omega. Your flux is ergs per second per centimeter squared. And if it is at a certain frequency, the specific flux density, then it will be per hertz. Okay, so if I were to express this at F is equal to I cosine theta d omega, because omega is what I put in terms of specific intensity per unit solid angle. All right, so flux is related to your intensity by this expression. And if theta again is the angle relative perpendicular to the area, and if theta is equal to 0, then cos 0 is equal to 1. And if I is assumed uniform throughout the source, then you can put the flux which you observe is equal to the intensity or brightness into the solid angle. Okay, F is equal to I omega. So the intensity is equal to flux divided by the solid angle. Okay, if you're talking of specific intensity or specific flux density, then it will be at a particular frequency or wavelength. But this is a more general expression of the intensity is equal to the flux density divided by the solid angle. All right. So just remember that this is a very basic definition which you should remember. All right. Now, let's look at the two situations. One is when we are observing with a telescope. All right. So as we just saw that F is equal to I omega, we put the telescope pointing at the source. So theta is of the 0 degrees. And so I put this cos 0 degrees as 1, and intensity, assuming it to be uniform, F is equal to I omega. Now, suppose I'm looking at the sun. I can think of the sun as being divided into many pixels, and each pixel subtends a small solid angle, say d omega I, okay, and has an intensity I, say, okay. So you can go and integrate this out from the whole surface of the sun to get the total flux density of the source. Now, because F is equal to I omega, if I cannot get an estimate of what the solid angle is, then I cannot get an estimate of I. I cannot define it. But if, for example, if a source is unresolved with a particular angular resolution, whether it be the seeing disk or whether it be the angular resolution of a radio telescope, okay, I'm not able to measure the size of the source. So I cannot define a solid angle for the source. I could only put in those cases, I can say the source is slightly smaller than my resolution element. And I can put a limit on the brightness, but I cannot have a precise value for the brightness. I can also estimate brightness from another angle, which is, I think during the talks that presentations that you'll made, one of you mentioned about estimating the size from the time scale of variability, because the maximum velocity with which a signal can propagate is the velocity of light. So that will give me a size scale from the time scale of variability. And if I know the distance of the source, I can convert it to an angle and I can get a steradian from it. So I can get it by indirect means. I can estimate what the intensity is, either put a limit if there is no other information except the resolution and it is unresolved, or from arguments as the ones we just discussed, that one can get an estimate of I. But ideally, you want to know the solid angle that the source subtends. Okay. Now, I want you to think for a moment and just tell me the answer to the question. Can a source of lower brightness, fainter, have a larger flux density than one of higher brightness? Just think for a moment. This is just to try and get your concepts of brightness and flux density sort of clear. I have a low brightness feature and low brightness emission, which is fainter. Can that have a larger flux density than a source of high brightness?
Yeah.
Sorry, Aham, go ahead.
Because we're talking about brightness.
Sorry?
We're talking about brightness here, which depends on your distance to the object.
Brightness is intensity, okay? Brightness is intensity, and intensity is flux density divided by the solid angle.
Sir, I think it would be possible for a source of lower brightness if it's closer to you as compared to a source of higher brightness that's further away. Then the source of lower brightness would have a larger flux density.
Okay. Okay. Anybody else who agrees or disagrees with Ahan's point?
I don't mean to say that if a body is closer, then it will have higher flux density, but
see, okay, let's look at this equation. F is equal to I omega. Okay, I is the intensity or brightness. Okay, that is what we have called brightness as the intensity of brightness. Okay, I is equal to F upon omega. Okay, now for a fixed surface like the sun, for example, say let's look at the sun, which is being shown over here. The flux density is going to go down as 1 upon r squared, right? And your solid angle, which is subtends, is also going to go down as 1 upon r squared. Solid angle is defined as omega is equal to area upon r squared. So you'll find that the flux density is also going down as 1 upon r squared. The solid angle is also going down as 1 upon r squared. So your intensity or brightness is not going to depend on distance. As long as, I mean, there is no absorption medium and the medium is sort of uniform and it's non-absorbing and okay. So your intensity is a parameter which is, or brightness is a parameter which is not dependent on distance. Okay. Because F is equal to the flux density will depend on distance, your solid angle will depend on the distance, and both depend on distance in a very similar way as 1 upon r squared. Omega is equal to A upon r squared. Flux density is equal to luminosity, proportion to luminosity upon r squared. So your brightness will be distance independent. Intensity will be distance independent. Now, given this, can you have a lower brightness or lower intensity source to have a larger flux density than one of higher brightness? Anyone?
No, sir.
Yeah, no, we can't have that.
Are you sure, Kriti? Now, what you're forgetting is that, for example, think of the radio galaxy which we discussed about earlier. Okay, Cygnus A. Okay, think of the image of Cygnus A, which has two hotspots at the outer edges and diffuse lobes of emission, right? Diffuse lobes of emission. Now, what those regions indicate are millijanskis per unit beam area. Beam area is the resolution element, basically. So that defines a solid angle. So you can see that the hotspots are higher brightness or higher intensity than most of the radio lobe. Okay, than most of the radio lobe. Now I can have the radio lobe is weaker. So I have a large region of diffuse emission. Okay, large area of diffuse emission. So I could, for example, if I were to look at this equation over here, okay, this equation over here, see, I could be much lower, but if the solid angles which I add up is over a much larger area compared to a higher value of I and a lower value of omega, I could get a larger flux density for fainter emission if it's spread out, for example, as I showed you, giving you an example, spread out over a larger area. Okay. Is that okay? Is that clear?
I'm actually still a little confused. This was a lot.
Okay, let's just go through it again quickly. Okay. So you can see over here that the flux density is the sum of the emission from an entire area. Okay. In this particular source, for example, what you have is you have a high brightness area over here. Okay. But the solid angle, this substance is very small. And the flux is, okay, is intensity into solid angle. You can think of it as one unit or you can break it up into different units. It doesn't matter. But you can see that the solid angle is small. Okay. The intensity is high. Okay. The brightness is high, but the solid angle is small. Brightness is low, but the solid angle is large. So your flux density that you estimate would be the summation of the products of different elements of the solid angle and the brightness. So because if the area is very large, when I keep multiplying by solid angle, by solid angle, I can get a much larger value of flux. Remember, flux is ergs per second per unit area, right? Per centimeter squared in the case of CGS units. Whereas this one, it may be high, but it is spread over, it's fixed to a very small area. So when you add this up by multiplying with the solid angle, the smaller value of total flux for this compared to a region of lower brightness. Does it make it clearer?
Okay, so it's basically because the lower brightness source might be covering more area.
Absolutely.
Is that okay? All right,
Absolutely.
now I get it.
Okay, absolutely. Because more area means the solid angle is larger, isn't it?
Right, yeah.
Okay, so solid angle is larger. So that is how a lower brightness region of emission can have a larger flux density than one of high brightness. So larger area means a larger solid angle, okay? Because you're talking of the same source over there. Now, I just wanted to introduce you another concept, which we talked about the flux, astrophysical flux from a source, okay, which is emission, radiation emitted from the surface of a star. And you made an estimate of it as well, which is the luminosity divided by 4 pi r squared. Okay. Now we want to relate the astrophysical flux to the intensity. Okay. Now, going back to the definition of flux over here, I cosine theta d omega. Now, I'll imagine a surface on the star over here. And let's say the radiation from an element of area on the surface of a star. But that emission can go out in all directions, right? It can go out in any directions. So when I think of an area over here, an elemental area from which the emission is going out, here in this case, when we talk about a star, it is emission going out. Whereas when I talk of a telescope, I'm receiving emission from a celestial object. So when I think of an astrophysical flux, F is equal to I cosine theta, angle at which the emission is going out relative to the perpendicular direction. And it can be going out in any direction. So I need to integrate this cos theta and over all solid angles. And the element of solid angle d omega has been expressed as sine theta d phi. And this goes from 0 to pi by 2. Okay, 0 is when it's orthogonal, and phi goes in any direction, so it is 0 to 2 pi. So if you integrate this out, okay, if you integrate this out, and I is assuming I to be uniform, you'll get flux of the emitted from the surface of a star is equal to I, the intensity, into pi. Okay, this will, you can cos theta sine theta, you can express it in terms of sine 2 theta, and then integrate it out. Pi goes from 0 to 2 pi, put the integration limits, and you will get the answer pi. So flux, radiation emitted in all directions. So when you're looking at the surface of a star, the flux, the astrophysical flux emanating from the surface of a star is related to its intensity by F is equal to I pi. Okay, that's a useful and important relation to sort of remember as well. This we have already discussed a bit earlier, that that the intensity or brightness is independent of distance, because both F and omega vary inversely as the square of the distance. But this assumes that there is no intervening absorption. Okay. So these are images of the sun itself taken from different by satellites from different distances, and the brightness per unit steradian. Once you put in per unit steradian, it is going to be similar or the same. Okay, you can think of it as when you get closer, you will get a larger, you'll get more details. You see a larger angular size of the star. You can think it of as a picture in your home as well. When you go closer, it will subtend. The angle which it subtends will change. But if you look at it as the emission per steradian, then you'll find that the brightness will remain the same. Okay, that is independent of distance. So that is an important concept to also just keep in mind. Okay, so what happened? Going back, it seems like. Now, just a few more slides, then we will stop. Okay. Now, so far, while introducing the concept of brightness or intensity, we have not actually talked about the physical process responsible for it. And if you measure a flux density and divide it by the solid angle, that is what we have defined as the intensity of the radiation. Now, in the case of a black body radiation, which you are all familiar with, I've written down the expression in terms of frequency over here, 2h nu cubed upon c squared, 1 upon e to the power of hd by kt minus 1. And this is the Rayleigh-Jeans approximation. E to the power of hd by kt is much less than 1. And then you can show that the brightness is proportional to 2 kt nu squared by c squared, okay, which translates into 2 kt by lambda squared. Now you've already estimated for the sun and showed it to be very small. And for CMBR, we did it the other day, and we saw that it sort of breaks down when you go to millimeter wavelengths and very low temperatures. Now what happens over here is that the brightness is given by a temperature. It's related to a temperature in the case of a black body radiation, okay, 2 kt upon lambda squared or 2 kt nu squared by c squared. Now, but you'll often find that radio astronomers particularly still talk of a brightness temperature even when there is no black body emission. So when you see the term brightness temperature for a radio source, do not assume that it is radiating like a black body. It is just that the brightness which they have inferred, they've translated it into a temperature using the Rayleigh-Jeans approximation. Okay. So using that, what you'll get is power emitted per unit area, per unit frequency, per unit radian of solid angle by a black body. I have used S nu here as commonly used at radio frequencies. I've used F nu earlier. This is just to state that I've used S nu over here because in radio astronomers often use this convention and denote flux density with the symbol S. So brightness is just S nu divided by the solid angle, and brightness, if you relate it to the Rayleigh-Jeans expression over here, you can get a temperature, and that is what is referred to as the black body, as a brightness temperature of a source. So you can see for the same source, the brightness temperature increases with wavelength, okay? Increases with wavelength. And this, and as I just mentioned, the radio astronomers use the term even if emission is not from a black body. And in fact, the brightness temperature has some useful physical concepts because there is a limit to the brightness temperature, which was calculated a long time ago. If it increases beyond about 10 to the power of 12 degrees Kelvin, then these inverse Compton processes take over. So it is good to know what the brightness temperatures of the objects are. And you can also know the brightness temperatures, for example, if it's an optically thick H2 region. So what kind of brightness temperatures would it have? If you can estimate a brightness temperature which is much greater than that, then it is possible that non-thermal processes are operating. And you can do that by, for example, you can get a very small estimate of the solid angle by going for VLVI observations, which is in milliarc second resolution, and get a small value of the solid angle and see what kind of brightness temperatures it has. And that gives you a clue as to what the physical processes in that particular object could be. This we have already gone through. This just gives you estimates based on that the flux of the sun at the surface. This is something which you all calculated very recently. And if you want to calculate the surface brightness of the sun, you have to just divide by pi, and that will give you 2.01 into 10 to the power of erg per second per centimeter squared per steradian. Okay, now this is a useful quantity because you can see that you can measure the brightness of an object without actually knowing the distance to the object. All you need is a measure of the flux density and the size of the object. That will give you an idea of the brightness of an object. And this has been used not only, I've so far talked about stars. I'll just give you one more example where brightness is used, and I will stop with that. This is the galaxy, irregular galaxy, Messier 82, which we have met earlier. It's a reasonably active star-forming galaxy in the central region. On the left is a HST image of it, and showing a supernova which had gone off in 2014 January. And on the right is a radio image of just the central region over here. And a lot of the compact components which you see are supernova remnants, which are remnants of massive stars which have exploded. Some of them are also compact H2 regions. And what you can do is you can measure the average surface brightness of this object. You can measure, you can know what the size is. you know what the flux density is, and you can see how that might change with time. It just gives an idea of how surface brightness changes with as the source evolves, as the supernova remnants evolve. And also there are suggestions that in dense regions, they have a higher surface brightness as they evolve compared to less dense regions. So these are just an example which I wanted to illustrate to you as to how brightness gets used even in other contexts, although we have discussed largely about stars today.